Hi everyone. So in this video, we're going to continue with Chapter 2, Functions, Equations, and Inequalities. Specifically, Section 2.3, Solving Equations and Inequalities. So we're going to start with equations involving a radical. So radical means a root. And let's take a look at example 2.10. It says solve for x in the following equation. Square root of 3x plus 6 equals 2x plus 1. So this is pretty simple. All you have to do is square both sides of the equation. Square both sides. And then we're going to get that 3x plus 6 is equal to 4x squared plus 4x plus 1. Then we bring all the terms to one side, and we're going to get that 4x squared plus x minus 5 is equal to 0. We factor this, and it's going to be 4x plus 5 times x minus 1 is equal to 0. So we have two solutions. One solution is going to be minus 5/4, and the other solution is going to be 1. But we always have to test these solutions to see which one works, especially when you have radicals. And if you test these in the original equation, you're going to see that this is false, a false solution. And this one is the only solution that works. So x equals 1 would be the only solution to this equation. So now let's take a look at equations involving fractions. And we're going to solve example 2.11. And it says, find all real solutions of the equation 2x over 4 minus x squared plus 1 over x plus 2 equals 3, and verify the solutions with a GDC. So whenever we're adding fractions, we have to make sure that we have the same denominator here, right? So notice that this is a difference of squares. This is the same as saying 2 minus x times 2 plus x. And notice that this expression here, this denominator, is the same as 2 plus x. So in order to get the same denominator for both expressions, all we have to do is multiply this by 2 minus x. So let's proceed to do that here as well. We have to multiply also the numerator by 2 minus x. So we are going to get the expression 2x plus 2 minus x over 4 minus x squared is equal to 3. So now we simply send this to multiply the 3, and we're going to get x plus 2 is equal to 3 times 4 minus x squared. Then we obviously simply expand this, right, and rearrange, and we're going to get 3x squared plus x minus 10 equals 0. So then we simply factor this, and it's going to be 3x minus 5 times x plus 2. So that means that we have 5/3 as a solution and -2. But this is not a solution. Why not? Well, because if you plug in -2 in the denominator here, you're going to get 0. And that then at that value, it becomes undefined. So therefore, the solution is x equals 5/3. So now we're going to use the GDC to verify the solution. Okay, so here we are with the graphing display calculator, and notice that I have plugged in the equation. Now, one thing you have to be careful with is the use of parentheses, right? Because if you want to write 2x divided by 4 minus x squared, you have to make sure that this part is in parentheses. Otherwise, the calculator will interpret it incorrectly. Then this plus 1 over x plus 2, and notice that I have now minus 3. Recall that this would equal 3, but what we want to do is bring the 3 to this side, and basically this equals 0, right? Therefore, what we're going to do is plot this and then find the x-intercept. So for that, we need to simply go to graph, and there's the graph. So this is the point that we need to find the intercept here. So let's use the second key and calculate, and 0. Let's use 0, option 2, and then it says left bound. So when it says left bound, that means below what we believe to be the x intercept, right? So go to the left, hit enter, right bound, go a little bit to the right, in this case a little bit above, there, hit enter. It's going to say guess, boom, and there it is, 1.6667, and this is obviously the same as 5/3. Therefore, the solution to the equation would be 5/3. So now we're going to take a look at equations in quadratic form. And let's study example 2.12. Find all real solutions of the equation 2m to the 4 minus 5m squared plus 2 equals 0. So notice that we could rewrite this as 2m squared to the power of 2 minus 5m squared plus 2. So notice that if we do a substitution, say x, let's say x equals m squared, we could rewrite this as 2x squared minus 5x plus 2. And of course equals 0 because that's what we have to solve for. So this is pretty easy to factor because this is simply going to be 2x minus 1 times 2x, times x minus 2. Okay, therefore the solution should be x equals 1/2 or x equals 2. But we already said that x equals m squared, so that means m squared equals 1/2 and m squared equals 2. So that implies that we have 4 solutions because m can be plus minus the square root of 1/2, which you can find in a different notation as plus minus square root of 2 over 2. And then the other solution would be m is equal to plus minus square root of 2. So in this case, we would have to test all 4 solutions, but I won't even test them in this occasion because this is to a power of, it has an even number as a power. So I'm pretty sure that all these solutions will hold. In any case, if you test them all, you're going to get that all 4 solutions are valid. So therefore, the solutions for m would be square root of 2 over 2, negative square root of 2 over 2, square root of 2, and negative square root of 2. We continue with example 2.13. Find all solutions expressed exactly to the equation w to the 1/2 is equal to 4w to the 1/4 minus 2. So when they want us to express the solutions exactly, it implies that if you get square roots, they want you to express the solution in square roots, not with decimals. The first thing we can do here is rearrange. And notice that we can rewrite this as w to the 1/2 minus 4w to the 1/4 plus 2 is equal to 0. And then notice that this is the same as saying w to the 1/4 squared minus 4w to the 1/4 plus 2 is equal to 0. If we make a simple substitution, say t is equal to w to the 1/4, then we could rewrite this as t squared minus 4t plus 2 is equal to 0. So notice that we cannot factor this. You cannot factor this. But one thing we can do is make it into a perfect square and then solve. So notice that I can make this into a perfect square by simply adding 2 here. But if I add 2 to this side, I should add 2 to the other side of the equation, right? So notice that now I have t squared minus 4t plus 4 equals 2. And this is a perfect square because this is simply going to be t minus 2 squared equals 2. So this is what's called completing the square. Now, if we rearrange this, if we try to solve for t, notice that we can do it this way. We can square root both sides. So it's going to be t minus 2 is equal to plus minus square root of 2. Therefore, t would equal 2 plus minus square root of 2. But remember that we said that t is equal to w to the 1/4. So w to the 1/4 is equal to this, right? 2 plus minus square root of 2. Uh, that means that we have to put both sides of the equation to the power of 4. And then we're going to get that w is equal to, let's separate the solutions, 2 plus square root of 2 to the power 4, and w is equal to 2 minus square root of 2 to the power of 4. So we still have to expand this, right? This to the power of 4. So one thing you could do is rewrite it or do it as w is equal to this expression squared and then squared again. And same here, right? And if you do that, you're going to get w is equal to 68 plus 48 square root of 2. And you're going to get the other solution, which is w is equal to 68 minus 48 square root of 2. This would be the solution expressed exactly. So let's continue with equations involving the absolute value, also known as modulus. And we're going to solve example 2.14. So it says use an algebraic approach to solve the equation absolute value of 2x plus 7 is equal to 13 and check any solutions on a GDC. Okay, so in the cases of absolute value, because this expression here can be positive or negative, it means that we have two solutions. So one solution would be 2x plus 7 is equal to 13, and the other solution would be that 2x plus 7 is equal to negative 13. So let's solve these equations, and notice that we're going to get that 2x is equal to 6, therefore x is equal to 3, and then here we're going to get that 2x is equal to negative 20, therefore x is equal to negative 10. If you plug these back in, you're going to get negative 13 here, and if you plug this in, you're going to get positive 13. But let's use the GDC to verify the solutions. Okay, so here we are with the GDC, and I'm going to show you how to plug in an absolute value function. So what you have to do is click on Math and then move one to the right, using the arrow key to the right, and go to where it says Num. And notice that the first option is absolute value. So click on 1, and there you go. There's the symbol for absolute value. So it's 2x plus 7, right? So 2x plus 7, absolute value of 2x plus 7. And it says this equals 13. So we have to bring the 13 to the left-hand side of the equality. So that means that this minus 13. Okay? And then this would equal 0. Therefore, what we have to do is find the x-intercepts. So let's do that. Let's graph. Take a look at the graph. Oh, we have to probably zoom out a little bit. So I'll teach you how to actually make the window a little more convenient. Yeah, because we need negative 10 as one of the solutions. So you can go to Window and notice that you have the x minimum at negative 8. So maybe you want to make this negative 20, and then let's say 20. And then for y, let's say the same, negative 20 and 20, just to be able to see the graph. Negative 20 and 20, and then graph. And there you go. So notice that we have two solutions in there. Obviously, just by looking at the graph, you can see that they are 3 to the right and negative 10 to the left. But let's verify that, right, using calculate. So let's go second key, calculate, and 0. And then it says left bound. So let's check this one out first. So enter, then we move a little bit to the right, above the x-axis. You have to do one below the x-axis and the other one above the x-axis. Hit enter, enter again, and there you go, 3. Let's do this again. So second key, and we want to find a 0. Now let's move to the graph. Let's do it above, right? Above, in this case, above, because it's the left bound. So hit enter. And then the right bound, we would have to go below the curve. There's a right bound. Hit enter again, and there it is, -10. Next, we're going to take a look at example 2.15. And it says, find algebraically the solution or solutions to the equations. Absolute value of 2x minus 3 is equal to the absolute value of 7 minus 3x. So absolute value equals another absolute value. And then check the solutions or solution graphically. So in these cases, it's not very different from what we did before. So here, what we would say is that we have two solutions or two probable solutions. One would be 2x minus 3 is equal to 7 minus 3x. And the other possible solution would be that 2x minus 3 is equal to minus 7 minus 3x. So let's solve for these. 5x is equal to 10. Therefore, x equals 2. And then for this one, we're going to get 2x minus 3. 2x minus 3 is equal to minus 7 plus 3x. And if we rearrange, we can get that x is equal to 4. So these are the two possible solutions for this equation. Now we can test it by plugging it back in and we'll see that they both work. But let's check them graphically. Okay, so here we are back with the graphing calculator. And notice that I have plugged in absolute value of 2x minus 3 and absolute value of 7 minus 3x. So in this occasion, I'm going to graph both sides of the equality, and then I'm going to find the intersects. So let's hit on graph. Here are the two equations. So notice that we have two different intersects. I'm going to change the window just to zoom in a little bit. And instead of minus 20, I'm going to have minus 10 and 10, both for x and y, just to have a clear picture of the situation. So that would be here, second key, and then calculate. I notice that option 5 says intersect. So let's do option 5, and it's going to say first curve, the blue curve. That's fine, hit enter. And then second curve, the red curve, hit enter. Guess, yes, and there's 1, right? At x equals 2. Let's do the other one. So we go second, calculate, and number 5, intersect. And first curve. Now here we want to get a little bit away from where we were before. Let's say right there. So enter, and then second curve, yeah, the red curve, and guess, and there it is, x equals 4. So the last part of this section is quadratic inequalities. And we're going to take a look now at example 2.16. And it says, find the values of x that solve the inequality x squared is greater than x. Now, it could be possible to determine the solution set to this inequality by using trial and error or a mental process. And it might be successful, but generally speaking, it's a good idea to try to find the solutions by using an algebraic method. So we can rearrange this and notice that you can rewrite this as x squared minus x is greater than 0. And if you factor this out, it's going to be x times x minus 1 is greater than 0. So from this, we get the critical values, 0 and 1. And with this, we can build what's called a sign chart. So with a sign chart, what we do is that we use the critical values that give 0, which in this case would be 0 and 1. And then we can test values that would be to the left of 0, between 0 and 1, and then to the right of 1. So to the left of 0, -1, we can test. And notice that if we plug in -1 here, we're going to get a positive value. If we plug in 0.5, we're going to get a negative. If we plug in something larger than 1, like say 2, we're going to get positive. So this gives us the intervals that solve this inequality, being that x would be less than 0 or x greater than 1. Finally, we're going to do example 2.17, which is the last one on this video. And it says, given f of x is equal to 3k x squared minus k plus 3x plus k minus 2 equals 0, find the range of values for k for which f has no real zeros. So recall that from quadratics, we know that if you have a discriminant that is negative, then this does not have any real solutions. The discriminant, recall, is b squared minus 4ac. So b squared minus 4ac has to be less than 0. Now remember that a, b, c are simply the coefficients of the quadratic function. So we can simply substitute for these values, and we're going to get that minus k plus 3 squared minus 4 times 3k, so 3k times k minus 2, and all this should be less than 0. So let's expand and rearrange this. So notice that we're going to get k squared plus 6k plus 9 minus 12k squared plus 24k. Should be less than 0. And then grouping similar terms, we're going to get minus 11k squared plus 30k plus 9 should be less than 0. Well, this is negative, so I don't like that. I'm going to multiply both sides by -1. And remember that whenever we divide or multiply both sides of an inequality by a negative number, we have to flip the sign. So this is the same as saying 11k squared minus 30k minus 9 is greater than 0. And this is factorable. We can factor this. Notice that this is the same as saying 11k plus 3 times k minus 3. This must be greater than 0. So the critical values are going to be minus 3 over 11 and 3. So we can build a sign chart using those, right? So let's build a sign chart. And here we have -3 over 11 and 3. And we'll do what we did before, which is test values before, between, and after -3/11 and 3. So -1 is to the left of this, right? So what happens if we plug in -1 here? Well, this would be negative, and this would be negative. Therefore, we get a positive. Let's plug in something between, like 0. We would get 3 times -3, that's negative. Let's plug in something larger than 3, like 4. 44 plus 3, 47 times 1, positive again. Therefore, that means that k, in order for f of x to not have any real solutions, k would have to be less than -11/3, or k should be larger or greater than 3.